So in this case, we're going to be talking about how to use nomenclature rules for transition metals. And it's similar to other binary ionic compounds. The name of the metal goes first, the anion goes at the end. If it's binary, we change that to chloride or oxide or sulfide. But transition metals are a little more complicated than elements in the S&P block because they can form more than one cation. And it's going to be very important to tell the reader which ion we're making, because if we have to balance out the charges, we can get very, very different formulas for different ions. And those different compounds can have extremely different properties. For example, iron can form two ions, iron 2 plus and iron 3 plus. Iron 2 plus is if I form iron 2 oxide, I get a black solid that can be even shiny, it's magnetic. But if I form iron 3 oxide, because of the different ratios needed to balance the charges on that compound, iron 3 oxide is rust. It's brown, it's flaky. It's not the same at all. So we really need to tell the reader which transition metal ion we're dealing with. And we do that by putting a Roman numeral in parentheses after the name of the metal. If you don't remember your Roman numerals, I'd suggest taking a second and looking them up through probably 5 or 6. It would be very, very rare to get anything higher than really 6 is probably the highest you'll ever need, which would be VI. So if you don't remember how to do Roman numerals, I'd suggest taking just a couple minutes to remember that or relearn that. So speaking of iron 2 oxide, that too, please key in on this. That too does not mean there are 2 iron atoms. It has nothing to do with the number of iron atoms except for giving me the charge that I need to balance out. So if you see iron 2, it does not mean that there are necessarily 2 iron atoms in that compound. Not even a little bit. What it tells me is the charge on the iron, that we must be using iron with a 2 plus charge, Fe 2 plus. Oxygen is in the P block. Oxygen is predictable as the day is long. Almost every time I see oxygen, it will form oxygen 2 minus. So if I have iron that is 2 plus and oxygen that is 2 minus, there's only one ratio that gets me a balanced compound that exists on the pretty green earth. It must be FeO. So it is not 2 irons. It is that every iron is plus 2. You must make a note of that. You must get that in your head. That's the biggest thing that people get wrong, is they get that Roman numeral and they say, oh, that means iron must be 2 irons in there. And then they're trying to figure out how on earth they can do anything. It does not mean there are 2. It means each one is plus 2. So getting the name from the formula, let's look at this titanium compound. It's a binary compound of titanium and oxygen. So on the base, it should be titanium oxide. But if we look at the periodic table, we see that titanium is a transition metal. So we're going to need to figure out what the Roman numeral is in the name. And we can't just guess. We know it has to cancel out. And we know what oxygen does when it forms an ion. We know it forms oxygen 2 minus. So we can use the anion that we know the charge for to figure out what must be the charge on the cation so that they cancel out and we have a compound that exists. So one way I like to do this is to write out the elements in the formula. So I make a little table. Here's my element, here's my charge. Titanium, well, don't know what that is, so I could write it as an X if I wanted. I could make this an equation. Then the O2 means I have 2 oxygens, and each one of those oxygens is -2. So I could even think about this as an equation that says X -4, because -2 and -2 is -4, X -4 must be equal to 0 because the positive charges must balance the negative charges. We have 4 negative charges, and the only way to get a positive charge is off of that titanium. So if X -4 equals 0, then X had better be +4. So if we look at the periodic table, there's titanium. We know it's a transition metal, so we have to put the valence in the name. And now we know that valence is 4 plus 4. So the name here has to include the Roman numeral. It's not just titanium oxide. This is titanium 4 oxide. It's really important that we do that because titanium II oxide is absolutely a thing. And titanium II oxide would not be TiO2. It would just be TiO because 2 plus balances out 2 minus. So we really have to make sure when we look at a transition metal that we are keeping our Roman numerals in mind. If only it were as easy as just being transition metals. So there are a few exceptions, not a ton, but a few that I very much suggest that you write on your periodic table. We'll get to them in just a minute, but let's do a couple of examples first. So here are 2 example problems. Both of them are transition metals. One of them, obviously cobalt is a transition metal, so you'll need to figure out the Roman numeral in the name. The other one is obviously a transition metal because there is a Roman numeral in the name. So I'm going to give you a minute or two to pause this and try it, and then check your work. Okay, so let's look at these problems one at a time. So if I have cobalt chloride here, since I know cobalt is a transition metal, I'm going to have to figure out what the Roman numeral should be. So like I said, let's break down the formula. 1 cobalt, we don't know what the charge is. We have 2 chlorines. Chlorines are always, chloride ions are always -1. So in order to make this balance, what does the charge on cobalt have to be? Again, you can think about it like a very simple equation. We know in the end we have to have 0. So this is essentially x -2 equals 0. Well, x -2 equals 0 is pretty easy to solve. To balance out that -2 total charge, cobalt must be +2. And that means that it's not just cobalt chloride, it's in fact cobalt II chloride. Yet again, please notice the 2 does not mean there are 2 cobalts. There are not 2 cobalts in there. Just because there's 1 cobalt does not make that cobalt 1 chloride. If that was cobalt 1 chloride, you'd be telling me each one of those chlorine atoms was -1/2, and I'd sure like to know how you got half an electron. The 2 does not give you the number of atoms. It gives you the charge. So we look at iron 3 sulfide. In this case, we have the information to get the charges. So the charge on iron comes from that Roman numeral. Since it's iron 3, each iron must be +3. So we can kind of do this the same way. We know that we have irons, and the irons are +3. We know we have sulfides. Sulfides are -2. It's right underneath oxygen. So this one isn't quite as easy as something like barium oxide where it's +2 and -2. But we know we have to make these two numbers equal to each other. So how can I make 3 and 2 something that will divide both? Well, I can take 3 times 2, that'll give me +6, and 2 times 3, that gets me -6. So that would give me 2 irons and 3 sulfurs. So I would have Fe2S3. Now, if you remember our crisscross rule from the earlier slides, yes, you could absolutely use the crisscross rule here. That would be an Fe3+. I'd put a 3+ up top. That would crisscross down and become the subscript on the sulfur. It's sulfur 2-, so the 2- on sulfur would crisscross down and get me the subscript on iron. The reason I did it this way was to show you why exactly the crisscross rule works. But always remember, if you use the crisscross rule, check to make sure your subscripts are in lowest terms. There's nothing that divides both 2 and 3 evenly, so we're good. So here are those exceptions that I mentioned. There are a couple of exceptions that do not use Roman numerals, even though they are transition metals. Chemists are lazy. If an element is always going to do the same charge, why bother writing a Roman numeral on it? So zinc, element number 30. Zinc is always, always, always +2. We talked about that a little bit on Monday of this week. Remember, zinc loses its 2 valence electrons out in the 4s. Once it loses those valence electrons, every other orbital is low energy, full, and stable. So notice cadmium right underneath zinc is also always +2 for exactly the same reason. Silver, element number 47, is always, 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 always +1. And the other one to remember is scandium. Scandium is element number 21. And you can see it's only 3 away from argon. So scandium and yttrium are pretty much always, always +3. Because if I lose those 3 electrons, I get back to argon. And there's no stability advantage to losing just 1 or, God forbid, 2. So there are the exceptions that do not use Roman numerals. Silver, scandium, cadmium, and zinc. I would write those charges on your periodic table. Put a little +2 next to the zinc and the cadmium. Put a little +1 next to silver. So you remember when you're using your periodic table that those are always that charge. So we don't need the Roman numeral. There are a few of the P block metals, the ones that are underneath that zigzag line, but in the P block, that actually do use Roman numerals. And they're the big ones down here: indium, tin, thallium, lead, and bismuth. You might wonder why not antimony? Well, actually that's because antimony is a metalloid. So in fact, it does sometimes use a Roman numeral, but sometimes it uses the rules for something which is covalent, because metalloids can act like metals or non-metals. So I don't want to make a rule that antimony must always have a Roman numeral, because maybe not. So it's important that you remember these exceptions. These 5 down here, the gang of 5, do have those multiple charge states, oxidation states, and we do need to make sure that we say what they are. There's a huge difference between lead-2 oxide and lead-4 oxide. It's important that we know which one we're going to be talking about. So let's finish up this part of the video by doing some practice on some ionic compounds. Again, I will give you a few seconds to pause this, and I will remind you to watch out for things that need a Roman numeral. All right, well, let's look at these answers. Sodium and iodine. None of those are transition metals, so it's just going to be metal and iodine, except we make it IDE. So that is nothing more than sodium iodide. Okay, we have strontium and oxygen. So strontium just stays strontium. Oxygen becomes oxide, not a Roman numeral because strontium is not a transition metal. So that is just strontium oxide. Keep going here. We've got aluminum, which is a metal, of course, and a nonmetal. So that's an ionic compound. So we have aluminum sulfide. Now, this is the first one that absolutely does need a Roman numeral. Manganese is a transition metal. That's not magnesium, that is manganese. So this is where I could use the same kind of rules like I did with the cobalt chloride. If I have two chloride ions, I have two negative charges. That means that my manganese here must be +2 to balance out the two negative charges from the two chlorines. So that would not just be manganese chloride. It'd be important that we say that that is manganese 2 chloride. Yet again, notice that the 2 does not mean there are 2 manganese. Oh my goodness. I cannot say that enough. So next one down here, this is a great spot to notice that potassium is right underneath sodium. And fluorine is in the same column as iodine. And notice that those two things have exactly the same ratio because remember, elements in a group behave similarly. So this would just be potassium fluoride. Here is our other common iron compound. We had iron II oxide, FeO, in the slides earlier. And I'll give you a hint that something you can do, again, as long as you don't turn off your brains, is you can do a little trick called the reverse crisscross. I can take that 3 and pop it back up where it came from. And that tells me that that iron must be iron 3. One thing to check though is make sure if you do a reverse crisscross that you make something that actually exists. See, because if I take this 2, that makes oxygen 2-, and that's absolutely what I know oxygen should do. So if I reverse crisscross this, that tells me that iron had to be 3+, and that is iron 3 oxide. The last one here is an example of where doing the reverse crisscross might trip you up because I will have people tell me that this is lead 2 oxide. It is not lead 2 oxide. The oxygen here is -2. If there are 2 oxygens, that means I have a total of 4 negative charges. So this is lead 4 oxide, not lead 2 oxide. And you can check that because if you tried to reverse crisscross this, you would come up with oxygen being 1-, which is a what sort of moment there. So if you try to do a reverse crisscross rule and you come up with a charge that doesn't work for that element, you need to think real hard about whether you should check and see if you had to reduce that. Or just go back to thinking, well, I have 2 of these and each one should be 2-. Sometimes shortcuts are great. Sometimes shortcuts can trip you up. So the last little bit of this is going to be on naming with polyatomic ions. Good news is that none of the rules we've learned in the last 2 videos really change at all.